So let's give some background since this is the first class, right? So let's start with the topic first. So what do we mean by nonlinear, right? When do we say some system is nonlinear, right? So how do we define any system, right? So this could be any general thing, not just an optical system. It could be anything, right? So some system of or some device or technology, right, takes in some input X and does some modifications to it and gives out some output Y, right? And let's say we can describe this by some function, some modification, right? So typically these could be, for example, functions of time. So your input is some signal, right? It's a function of time, so it could be voltage, current, electric field, what have you, right? And the output is also some function of time, and the system basically for different inputs gives you different outputs, right? And the way we define a linear system is, so let's say I give an input x1, it gives me an output y1. I give another input x2, it gives me output y2. Okay, for a linear system, if I give any linear combination of the two inputs, so some a times x1 plus b times x2, right? So a and b could be any constants. Then if the system is linear, the output would be a linear combination of the corresponding outputs, right? That's what a linear system means. Okay, and anything which violates this would be nonlinear, right? So it's important to understand first what we mean or what we mean by nonlinear, right? So this property has, I mean, you would maybe hear in some other courses or some other scenarios, this particular property is sometimes referred to as two properties. So one is, so let's say if x2 was 0, then if I scale my input by a times, then my output also scales by a times. Okay, so that's called a scaling property or homogeneity, also sometimes called homogeneity, right? And then this plus part. So if I add two inputs, I get the sum of the corresponding outputs. That's called additivity. Right? So basically a linear system is one which satisfies these two properties of homogeneity and additivity. So if I scale the input by a particular factor, the output also scales by that same factor. If I add a bunch of inputs, the outputs also I would save bandwidth and allow everyone to have a good streaming experience. And just keep your mics muted. Whenever you have a question, you can unmute and ask. Yeah, right. So you can think about what this function needs to be, right? This f of x, y, what this function needs to be to satisfy these properties, right? So naively you would think, okay, yeah, linear system means there should be some linear function, right? Y equal to x plus. But I would urge you to think more about it and look at these properties and see if is this system linear for all values of MNC. So think about that. Okay, so nonlinear system is one which does not satisfy this, right? So if I give some linear combination of the inputs, I do not get a linear combination of the output, right? Equivalently, this function would be some nonlinear functions. Okay, so it won't just have linear term of x. It will have some nonlinear terms. It could be whatever. Anything different from x to the power of 1 is nonlinear, right? And you can check for any such function, it would not satisfy these properties, right? And such systems would be nonlinear, right? So what does that mean, right? So you can imagine. So let's say you have one input. So for mod, this would be nonlinear, right? So let's say you have one input. If you send it by itself, x1, you get some output y1. If you have the other input, x2, you get y2. Now let's say I send in x1 and x2 together, I just don't get the sum of the two, right? So you can imagine you can do things like, for example, let's say I'm sending x1, it's giving me some output y1, and then I can control the output by sending another input, right? So depending on how this system behaves, I can, for example, increase y1 or decrease y1, do whatever I want by adding another input, right? For a linear system, that does not happen. The other input just changes the other component of the output, right? So, in other words, you could do something what is called switching, right? So you could switch one output, let's say y1 on or off, high or low, using another input, right? So that would be some switching sort of behavior. The other thing you could do with such systems is generate new frequencies, right? So as I said, these are functions of time, right? So let's say my input is some sinusoidal signal, right, at a particular frequency. So for linear systems, you can check that the output will also have the same frequency, right? So for example, you could have some of different frequencies, but it doesn't matter, you'll get the same frequencies at the output. Right? Again, going back to this kind of response. But if you have a nonlinear response, so just to take some example, right? So let's say this f of x was x squared, right? So then for a sinusoidal input, let's say cosine omega t, my output is cosine square omega t, which I can using the sine cosine rule. I can write it like that, right? So basically, you can see here now, and in the output, I have a frequency which is 2 omega, while my input had only omega, right? So now my output can have frequencies which are not present in my input, right? So the other thing you can do with nonlinear systems is generate new frequencies or wavelengths in the optics viewpoint, right? So in the photonics or optics case, mostly this is the application that we use it for, right? New frequencies means new wavelengths means new light sources, right? That's sort of the main application, but there are some applications where we can also do some kind of all optical switching for it. So one application of this that you see or you can see almost every day is your green laser pointer, right? So if you open up your green laser pointer, right, inside you will see that most of the space is taken up by like AA batteries or something, right, 2 AA batteries, and then there's a small amount of space inside which you have a nonlinear optical device. Okay, so why do you do it using nonlinear optics, right? Why can't we just have, let's say, a green laser or green light source, right? So problem is that you don't have materials which have band gap in that region, which we can, for example, grow in nice defect-free layers and make it into a semiconductor laser, for example. Okay, so there's just no way to directly make a green laser. I'm hearing some background, so everybody please mute your mics if, like, whenever you're not speaking, just mute your mics, please. Right, so yeah, the easiest way would be just to have a green laser, right? So for example, if you look at your red laser pointer, that just has this, would be, right, so for the red laser pointer is just a red laser, right? So semiconductor laser which lasers at some red wavelength, like 680 nanometers, right? So it's a
Sir, can you please
laser. But
explain
for
that green laser point? Because some noise
yeah,
was there, so not able to hear that.
yeah, I'm still on that point. On that point. So I'm first going to a red laser pointer. So if you use a red laser pointer, the red laser pointer has just a semiconductor laser which directly produces red light. Okay, so it has the band gap of the right value and it emits light at the wavelength around, let's say, 680, which gives you red. But for green, the problem is we don't have materials to make a good laser at green. Okay, in fact, it's very hard, and that's still an active area of research. So, if you want green, right, then you can't directly just make a laser. So, for green, what is done is that if you sort of zoom into this portion, you have three sort of parts. One is you have something called like it's a laser diode which emits at around 800 nanometer. Right, so that's the first part. So that's this like a semiconductor laser diode. So you bias it at some voltage, pass current, electrons and holes combine, and give out light around 800 nanometer. Right, that's used to pump another crystal. Okay, um, the second crystal, like it has some gain medium and it gives it gives out light. So it's pumped using this 800 nanometer and it emits light at around 1 micron. Okay, so this is wavelength. Right, so you're basically sort of using an 800 nanometer laser to pump another gain medium and get light out at 1 micron. And then you use a nonlinear optical crystal, okay, which does this function. Okay, so that crystal has some properties. Specifically, it has a second order nonlinear susceptibility. We'll go into susceptibilities soon in the course. But so basically, that material does something like this. It squares the input, right? So that means you get a twice frequency at the output, which means the wavelength is half, right? So then, after the nonlinear crystal here, your wavelength is about half of 1 micron, so that's about 500 nanometer, which is green. Okay, so I mean exactly this is like 1.06 and this is 530. Right, so in a sense what you're doing is you're taking a 1 micron laser and then frequency doubling it to get green. Okay, that's how your green laser pointer actually works. Right? So nonlinear photonics means like we're looking at optical systems, right, which are nonlinear. Right? So in optical systems, these inputs and outputs would be optical fields, right? Electromagnetic waves at optical frequencies, right? So laser light, for example, right? And you can see that these systems now will allow you to sort of engineer the passage of one laser beam through a medium using another laser, right? You can control, and you can generate new frequency and new light sources. Just to give you some history, So don't worry if you can't like note down everything right now. These lectures will be recorded and be put up on Impartus anyway, so you can take a look at them anytime. Right. So some history, right? So when so 1960 laser was invented. Right. So this was, remember, this was a ruby laser which emitted at around 690 nanometers. So it was a red laser. That was the first laser which was invented, right? And then, so once the laser was invented, basically you had a light source which was coherent, right? And it could be propagated over long distances. You could go to very high powers and intensities, right? And that enabled people to see nonlinear effects immediately, right? So it wasn't as if nonlinear materials which behave nonlinearly didn't exist, right? It just was that our measurement techniques were not capable of measuring them. So once the laser was invented, immediately, like a year later, the first nonlinear effect was seen, which was basically frequency doubling, this that I talked about, or the wavelength being reduced to half, right? So they were basically, I mean, that was immediately after the invention, almost immediately after the invention of the laser. So basically, the only laser available was this UV laser, right? So what they did was they took this UV laser, which emitted at 694, right? And then focused it to a tiny spot inside a quartz crystal, right? So, I mean, you know that the intensity goes as power over area, right? So the smaller you focus, smaller the spot area, the larger the intensity, right? And we'll see that the nonlinear effects scale with intensity in a nonlinear fashion, right? So high intensity helps a lot. So you focus it into a quartz crystal, and then they had a photographic plate after the crystal here. So what they saw, so if you just have a linear effect, then what you will see is basically just sort of the main laser beam coming out, right? So you will see a bright spot here. I mean, there might be some speckle on it, there might be some absorption and scattering, etc., etc. But basically, you see this the same wavelength at the output. But what they saw was at a slight angle to this, there's a very, very faint spot, right? So slightly away from the main laser spot was an extremely faint spot, and if you send that, or if you measure the wavelength, send that to a spectrometer, for example, they measured the wavelength of that tiny faint spot to be 347 nanometer, which was exactly half of my input wavelength. Okay. So that was the first time they observed any nonlinear effect. And I posted a link to this paper in Moodle, and so where they actually show this picture, right? And actually, there's a funny story associated with this. So what happened was, this spot was super bright, right? And this was very, very, very faint because this was the first experiment, right? First laser. They used to go use some material. They didn't engineer everything to be optimal. So this spot was extremely faint, right? It was so faint that, so when they sent the paper to the editor, or like after the reviews, the editor saw the paper. So this was in physical review, and the editors actually thought that this spot was like a smudge by mistake. So they just saw they thought that the main figure was just this main laser spot, and this some dot on the side is some ink drop or some mistake, and they actually smudged out this part. So even if now, if you go, I posted a link to the paper, you go to the paper and see the figure, you actually can't see this part because in the published version of the paper they actually smudged it out. So it's a funny story. Okay, and then after that, basically the field has exploded, and nowadays there are, I don't know, hundreds and thousands of papers on nonlinear optics published like every week. There are a lot of different journals, etc. A lot of different research groups. So it's really exploded. I posted a link to sort of a general article on how the field of nonlinear optics developed after this and how things sort of exponentially took off. So it's also interesting reading. So I'll urge you guys to just keep regularly checking Moodle. I'll post interesting stuff there. I also post reading sections from the textbook that are related to the material we covered. Right? So please keep checking Moodle regularly. Okay, so maybe let's start in earnest now. Go into the technical details. Right, so in the optics or photonics context, what do you mean by linear systems? So we talk about a system with input and output, right? So the output for optical system that we are looking at, so the input is of course some optical wave that we send into some medium, right? So the input would be some optical wave, electromagnetic wave, right? So you can take the electric field corresponding to that as the input, right? So that this corresponds to my x, right? And then the y that we look at is the polarization in the medium. Okay, so if you remember from your undergraduate electrostatics or electromagnetics, right? So if you apply an electric field to some dielectric medium, you separate the charges, right? And you create dipoles, and the dipole moment per unit volume is this polarization, right? So this is polarization induced in the medium. This is the electric field applied. Right, so polarization is basically the dipole moment per unit volume. Right? So you create these dipoles and per unit volume, that's the polarization. And if it's a linear system, then P is just proportional to E, right? And the proportionality constants we typically write like that. So epsilon naught is the vacuum permittivity, and there's this constant called chi. Right? This is known as a susceptibility. Right, so that's characteristic of the medium. Right, and if you remember, this is what gives rise to the dielectric constant. So if I write the electric displacement D, that is written as epsilon naught E plus the polarization, right? And if I plug this for the polarization into there, then I can write B as times E, right? And this constant I define as the material's permittivity, right? So 1 plus chi is the relative permittivity of the medium. Okay? So I've drawn some wavy lines here. So in the course, some notations, basically this wavy line would denote some fast varying quantity, right? Of course, these relations could hold in general for example, a DC applied field, right, or a field varying at some particular frequency, right. So in the optics case, typically these fields would be varying at the optical frequency, right. So hundreds of terahertz. So this tilde basically denotes that this is some fast time varying quantity. So whichever quantities will have these tildes above them would be fast time varying quantities. Okay, that's this, and these are constant. Uh, right, and so that's the linear case. The polarization induced in the medium is proportional to the electric field applied, right? So it's something like pi to mx kind of relationship, right? And to be more technical, this pi is generally denoted as pi 1, or the first order susceptibility. Okay, so in the nonlinear case, what happens? Of course, you can guess that now it's not just linearly proportional to the electric field, but you could have other terms, right? So in nonlinear optics, what we do is say that, okay, let's say I crank up this electric field, right? For low values of electric field, this approximation is very good, but as you keep increasing the electric field, the medium starts behaving nonlinearly. Okay? And then we have to add some extra terms here to more accurately model the material response. Okay, so the simplest way of that would be, for example, to add higher order terms of E, right? So E square E cube, and then proportionality constants would be so pi 2 pi 3. Right? That's why I put the 1 here. So the first order is called the linear susceptibility, and these higher orders are nonlinear susceptibilities. Right? So this is second order susceptibility, third order susceptibility. So you can think of this as some kind of Taylor expansion. Okay, so if I write this like so take one factor of the electric field outside and then write it like this. Okay, so basically, first term is constant, second term is proportional to E, third term is proportional to E square. So you can think of this. So if I compare this expression with the original expression that we typically use, right, for linear media, for example. So epsilon naught times E, and then the other factor is the susceptibility. So you can think of this whole thing as some nonlinear susceptibility. Right, and basically we are expanding that nonlinear susceptibility as in a Taylor series, right? So we are expanding it as a function of the electric field applied, divided by some constant which I call E atomic, right? So that's, in some sense, you can think of this as the atomic electric field. Which is the field felt by the electron inside the atom, right? So the nucleus is positively charged, it's putting some force on the electrons, and that's what's holding them, right? In the classical model. And the electric field experienced by the electron in the atom, you can think of as the atomic electric field, right? And this other E is the one which we are applying from outside, using some optical field, for example, right? So so you know that Taylor series expansion we can do when the argument is small, right? So, right. So you can do a Taylor expansion of some function f of x as some. So let's say I'm Taylor expanding about 0. So then f of 0 plus then the first derivative times x plus second derivative and like square. I can do some Taylor expansion like that, right? Provided this argument x is small, right? So that x is small, I can do this Taylor expansion. So similar argument holds here, right? This expansion is valid as long as E over E atomic is small. So in the case when an applied electric field from the optical wave is much smaller compared to the atomic electric field, we can use this Taylor series kind of expansion. Right? And we can estimate the atomic electric field simply by, I don't know, like, let's say the electron is at some Bohr radius from the nucleus, right? So the atomic electric field I can just estimate like that. Right? E is the electronic charge, A naught is the Bohr radius. Okay? So if you put in typical numbers, right? So Bohr radius is about an angstrom, 10 to the minus 10 meter. Right? You know, electronic charge, all these are constants. The value that you get is about 5 times 10 to the 11 volt per meter. Okay, that's sort of the order of the electric field felt by the electron in the atom. Okay, so as long as the laser fields or any optical fields that are applied to the medium, the electric field corresponding to that electromagnetic wave has amplitude much smaller than this, then this is valid, right? And in most cases, this E is actually so small that these are actually negligible, right? And you can neglect all of this, just the linear term. But once the intensity of the optical field or the electric field increases a little bit, such that you cannot neglect these terms, right? So E would still be much smaller than E atomic, but not sort of negligible. So you see some actual measurable effects from it. Then you have to include that. Right? So then these nonlinear susceptibility typical values. So the linear susceptibility typically varies in the range from unity to 10, right? So free space or air has susceptibility 1, right? And most dielectric materials have susceptibilities in this range 1 to 10. And 1 plus susceptibility is basically the dielectric constant. So you can, that basically gives you the range of the dielectric constant of most materials, right? Right, and chi1 is unitless. From here, right, chi1 is unitless. So P has, chi1 is a constant, it is unitless. Like epsilon naught has some units, P has some units, T has some units. But chi1 is unitless, right? Which we can also see from there. The chi2. So what units would chi2 have? From here, can you guess what units chi2 will have? Anybody wants to shout out? Right, so chi2 should have units of 1 over the electric field. Right, so this has units of electric field. Right, all these terms should have units of electric field, only then we can add them together. Right, so this one, chi1 is a constant, so this has units of electric field. This also should have like units of electric field. That means one of the orders should be cancelled by chi2. Right, so chi2 should have units of 1 over the electric field, which you can also see from here. Right, so the term corresponding to this is 1 over E atomic. Right, so chi2, as a rough estimate, you can see 1 over the atomic electric field, and the value is about 10 to the minus 12 meter per volt, which are inverse units of electric field. Right? And then chi3 by extension would be 1 over E atomic square. Right? So it has square, units of square, 1 over square of the electric field. And this will now be even smaller, 10 to the minus 24 meter square per volt. Right? So the values in SI units keep dropping down as you go to higher orders of susceptibility. Right? Dramatically. Which also makes sense because you want to do a Taylor expansion. Right? So, in general, what does that mean? That it's more difficult to see higher order nonlinear effects. So we can also estimate the laser intensities. So electric field, of course, is not very easy to measure directly, right? So let's say you have some light source, you can measure the power and you can measure the intensity easily, right? And from that sort of we back calculate what the electric field is, right? So typically we want to convert these to units of intensity or power. So intensity, again, if you recall your basic electromagnetics, is related to the electric field like that, right? So let's assume some plane wave traveling at the speed of light, right? So the intensity of that wave, right? So it's related to, for example, the energy density, right? So that's half epsilon E square. Then C is the speed at which it's propagating. So the intensity is related to the electric field like that, right? So we can estimate, so for example, let's say I wanted to have an optical source which has an intensity which corresponds to the electric field of the atom. Right, so that would be like, that would E atomic here and then get the work on intensity. So you would see that comes out to be about 10 to the 16 watt per centimeter square. Okay. So as long as the optical field that I apply or optical fields that I apply to my medium have intensities much lower than this value, then this kind of analysis holds. Right, and this is actually a very huge number. So just to get some idea, right, so typically, let's say the lasers we have, what kind of intensities can we obtain and how does it compare to this, right? So let's say you have some laser source, right, and it gives out some power, and then let's say you have some great optics, and then you can focus down this laser to a very tiny spot size, which is, let's say, diffraction limited, right? So the smallest spot size that you can focus the laser down to is sort of lambda square, right? That's the minimum, that's the average diffraction limit. So let's say you could focus down spot to that. So then the intensity at this spot would be the field, so power divided by the area, which is lambda square. Right. So the most common type of laser which is most widely used are semiconductor lasers. right? So these are used everywhere. For example, in optical communication systems, in your computer hard drive, laser pointer, what have you. So typical powers that these can give is about 10 to 100 milliwatts, right? And let's assume, just for simplicity, like wavelength, let's say around a micron. Of course, you can have a range of wavelengths, right? Like all the way across the visible or IR. So, but just to take some representative number, let's say the wavelength is around a micron. So the spot size here is like a micron square. Right, so for semiconductor lasers, this intensity would correspond to about 10 to the 4 watt per centimeter square. So you can see that's 12 orders of magnitude lower than the atomic electric field, right? So it's actually very difficult to see nonlinear effects with these kinds of powers. Although later in the course we'll study that how you can engineer things such that you see appreciable nonlinear effects even with such ones. Okay? But yeah. Then there are bigger solid state lasers. Right, so ND YAG or titanium sapphire, if you've heard of these materials, they can give higher power, so in the watts range, 1 to 10 watts, let's say. Right, so you can boost the intensity, let's say by a couple of orders of magnitude, go to like 10 to the 6. So these are typically what are known as CW lasers, which means that the power is constant, the output power is constant as a function of time. Right? But then you can have pulse lasers, where the output here is sort of pulsed. So you get nothing for a long time and then a huge spike at periodic intervals. Okay? And with pulse laser, basically what you're doing is sort of integrating the power in this entire time period and then dumping it in this very short time. Right? So you can imagine that if you have a very short pulse compared to the time period, then this power here can be really large. Okay? So with pulse lasers, you can get peak powers which are much larger. So there is something called femtosecond short pulse lasers. Basically, where this pulse width now is sort of in the femtosecond range. So let's say 100 femtoseconds or something. Right? Femtosecond is 10 to the minus 15. So that's a really short time. With this, you can get the peak power in the pulses up to like a megawatt, so 10 to the 6 watts. Right, so you can see that I can get intensities now which are say 10 to the 11. Okay, so that's sort of now say 4 to 5 orders of magnitude lower than the atomic. So with these, it's very easy to see nonlinear effects. And then you can build bigger and bigger laser systems. So there's something called amplified systems, regenerators, etc., which are basically like huge room-sized lasers. And the sort of state-of-the-art, these are like really big facilities. Which combine sort of multiple lasers together, and the record sort of currently is about like 10 to the 15 watts. Okay, so these are, for example, used in laser fusion, etc., or experiments on laser fusion. It's not at the stage where it's feasible yet, but you have. So these are really big systems. Like for example, the US has one or two of these systems, the Europe has one or two of these systems. So very um, costly, big, huge systems, but people have been able to reach that kind of powers. Okay. So with that, you can actually sort of exceed the atomic electric field, right? So you can, people have been able to reach sort of intensities of 10 to the 20. So by many orders of magnitude, you can actually exceed the atomic electric field, right? So that's why they use it for like that. At that point, basically, you just rip apart the atom, right? You ionize all the electrons, and then yeah, you can start doing fusion and things like that, right? So then you're not here. You're not in the nonlinear optics regime anymore, right? Because basically you destroyed your system. All electrons have been stripped away, right? And so these kinds of systems, so up to here you're sort of in the perturbative regime of nonlinear optics, basically where that Taylor expansion is valid, right? So basically, most of the sort of small scale experiments that people do, so I would say more than 90%, 95% of the research done in this regime. But then there are these really huge systems, right? Which are also. So, but then here you go to the non-perturbative regime. Where basically that you can't write the polarization as a Taylor expansion in the electric field, right? Then the system becomes really complicated. And one interesting effect that people see here in the non-perturbative regime is called high harmonic generation. So we discussed briefly, for example, frequency doubling, right? So basically, you send in a particular frequency, at the output you get the double of its frequency or half the wavelength. So that's second harmonic generation, right? So it's doubling. Second harmonic. And similarly, for example, you can imagine the third order would give you third harmonic, etc. Right? But in this non-perturbative regime, people have seen that you can generate, for example, 100th harmonics or even like 1000th harmonics. Okay. So you can generate, so you can start from, for example, an infrared laser and then generate X-rays. Okay. Through this phenomenon of high. But that goes into the non-perturbative regime, where basically all orders of susceptibilities are working together. You cannot actually write them as chi 2, chi 3, chi 4. That it's a more complicated effect, but that's one interesting thing that people see. Right? Because otherwise, for X-rays, you need some really big synchrotron facilities where you accelerate electrons to near the speed of light and then collide them with some targets, right? So typically, X-rays required huge resources, but with this, basically, all you require is like high power laser. But in this course, we won't be discussing the non-perturbative part, right? So most of this course will be just the, or all of this course will be the perturbative part, right? Which is, as I said, like 95% of the field of nonlinear optics. Right. So we saw that basically what's happening is we're generating polarization. Right. So if I take away the linear part, which is the first part with constant susceptibility, then I have terms which are going as the square and cube. of the electric field, right? So I can club all of that and call that some nonlinear polarization, right? So as I said, a nonlinear system can generate new frequencies, right? But how does that actually happen in an optical system, right? Because here what we are looking at, so E is the electric field of the input optical wave, right? And that is inducing some polarization in the medium, right? But how does that lead to, what I'm interested in is some output light coming out, right? So for example, that green laser pointer, I'm sending in some IR light, and then I want some green light output, right? But here, what we are talking about is just the polarization induced in the medium. So how does that translate into actually electromagnetic radiation is, so we'll see this in the next couple of classes, is basically if we try to write a wave equation for the electromagnetic field in the medium, you'll get this kind of expression, right? So this is sort of the typical wave equation that you get, right? So the spatial part and then the time derivative or derivative, right? So this is sort of the wave equation. And then on the right hand side, typically you have the source part, right? So for example, EM waves in free space, you put the right hand side to 0, right? If you have some charges or currents flowing, then you would have some source term, right? So here, basically what's happening is that the nonlinear polarization in the medium acts as a source term, right? So it actually generates electromagnetic waves. We'll see how this equation comes about in the next couple of classes. But for now, basically the point is that this nonlinear polarization acts as a source which gives out electromagnetic waves, right? So, for example, the frequencies in the nonlinear polarization will get translated to the frequencies of the radiated electromagnetic radiation. And another interesting point to note here is that you get a double time derivative. Okay, so it's the d square by dt square of the nonlinear polarization. So does that make sense, or does that seem very strange? Does it relate to some basic concept that you studied in your again basic electrodynamics? So fundamentally, how is electromagnetic radiation generated? Right, so let's say you have a charge, positive, negative. If I move this charge around, right, so it's like a current, right, that can give rise to electromagnetic radiation, right? And when does actually electromagnetic radiation happen? When this charge is accelerated, right? So if you have a charge which is moving at constant velocity, it doesn't radiate anything. But if it's accelerating, so if it's changing its direction or if it's changing its speed, then fundamentally, again from Maxwell's equations, right, you see it radiates electromagnetic energy, right? So you can see that this d square by dt square is like an acceleration term, right? So this polarization is basically the dipole moment, which is charge, right? And you're taking the double time derivative, right? So you're looking at the acceleration of charge. So that's where it's fundamentally coming from. Right, so these little dipoles in the medium that are induced, they're oscillating at some frequencies, and those oscillating dipoles radiate new electromagnetic fields. Right. Another point to note here is that these nonlinear susceptibilities, so some nth order susceptibility here, right? They are actually tensor quantities. right? Why? Because P is a vector, right? It's a dipole moment. E is also a vector, right? So you could take combinations of different directions, right? So for example, you could look at what is the polarization induced in the x direction due to the electric field, let's say one component in the y direction and one component in the z direction, right? So I could have different combinations like this. So there would be different indices, right, which denote that particular susceptibility, right? So tensor is basically a mathematical object which are sort of higher dimensional vectors, right? So vector has one index, so it could be, for example, P could be Px, Py, Pz, right? So I could write P with some index I. This I could take either x or y or z, or sometimes it is written as 1, 2, 3. Okay? So depending on what this index is, it will denote the vector in that direction. Right? So tensors are objects which have more than one index. Right? So for example, if I just look at the okay. So if I look at, like, let's say the first order or the linear polarization, right? That goes like that. So now P and E are vectors. I could take any direction out of the 3 for P, any direction out of the 3 for E, right? So I call this direction I, this direction J. So the susceptibility would have indices Ij. Okay, so susceptibility has two indices now. So it's a tensor, right, of rank 2. Rank means the number of indices. Right? So the first, so the chi n is a tensor of rank n plus 1. Right? So the first order susceptibility has two indices. Right? And this is nothing but basically anisotropic materials. Right? So I don't know if you've seen this before, like you can write the permittivity matrix as some EXX, EYY, ZZ, right? Some EXY, EXX. Right? In general, you can write a permittivity like that. Again, so this is defined as some tensor quantity, right? So depending on which direction you apply the electric field in, the displacement acquired in some direction is given by that particular index. Okay. So that's, so we saw epsilon is basically 1 plus chi. So that's what this chi I J is, right? So the first, the linear susceptibility has two indices. Right. So for isotropic materials, for example, all the non-off diagonal terms would be 0, only diagonal terms, and mostly if the material is also isotropic, then those values will also be 0. Right. But you do have some anisotropic materials where some of these are different, some off diagonal terms might also be present. Right. So now, if you extend this to second order, so I look at the second order susceptibility, so I'll use this term, right? So P bracket 2 denotes second order susceptibility. Again, so now polarization is a vector, so I have one index, so I denote Pi. So on this side I have epsilon naught chi 2, and then I have E square, or two terms of E, right? So I can choose. So I have two terms of E. I can choose one index J for one of them, K for the other. Okay? So for example, this J could be X direction, K could be Z direction, right? Or both could be X direction. Whatever. So now you can see that this needs to have three indices, I, J, K. Right? So chi2 is a tensor of rank 3. Similarly, chi third order, chi 3 is a tensor of rank 4. Right? So you can see that you have so many different terms, right? So how many terms do they have? So chi1 has two indices. Each of these index can take three values, right? The three directions x, y, z. So 3 into 3. So you have 9 different elements for chi1. Right? You can see for chi2 it will be 3 cubed. You have 3 indices, each of which can take 3 values. So that's 27 values. Right? And then for chi3 it's 3 to the 4th, which is 81 values. Right? But due to the symmetry of the material, many of them are either 0 or equal to each other. Okay, so you don't need to keep track of so many. So for most practical materials or real life materials, just from the symmetry of the material, either most of them are 0, and the non-zero ones are many of them are equal to each other. Okay, so we'll see a little bit more about that. Okay, so most of the nonlinear effects are those described by terms up to third order. Okay, so very rarely, I don't know, like maybe 1 in a million or not even, you will see higher than third order. So I would say 99.9% of the work done so far is up to third order. Okay. And it turns out to see second order, your material needs to have some special properties. Okay, so you can't see chi2 in any material you take. So to illustrate that, so let's write in terms of the tensor notation. So the second order, we are looking at the second order term. Second order polarization can write like this. So you can think of this as I'm applying two fields. One of them is in the j direction, one of them is in the k direction, right? And they induce a polarization in the I direction. Okay, so I have some material here. To choose any directions, right? X, Y. So each of these I, J, K could be either X, Y, or Z. Right? So I mean, it could be any configuration, but let's say for example it's this configuration. So you have some medium, you have some, let's say, arrangement of atoms, right? And you apply some fields, you induce a polarization. Okay. So now let's look at the case where the material is what is called centrosymmetric, which means it has a center of inversion, right? So I can take some point as origin and then flip all the atoms about that origin. So you can imagine, for example, I denote each of these atoms by some coordinates, right? So x, y, z. Each atom can be denoted by some coordinates. So a material which is centrosymmetric means that basically I invert the coordinates of all the atoms. So I take all the atoms here, put them here, take all the atoms from here, put them there, right? Invert them about the origin. If the material looks the same after I do this, then it's called centrosymmetric. Okay, so most materials fall under this category. Right? So, for example, let's say you have just solid with one atom, for example, right? So all the atoms are of the same type. It arranges itself into some periodic arrangement. If I reverse all the atoms, nothing happens because all the atoms are the same, right? So a piece of silicon, for example, right? And automatically, like if you have any liquid or gas, that would already be centrosymmetric because on average, you have all these molecules or atoms just floating around, right? So on average, it's sort of a smear on both sides. So yeah, there's no difference on one side of the origin or the other side. Okay? Uh, but you could have complicated materials which are made up of multi atoms. Again, amorphous solids like glass, for example, again have some random arrangement of atoms, right? So on average, uh, they look the same everywhere. Okay, so they are also interesting. But you have a small number of materials which have some complicated crystal structure and have multiple elements in them. Okay, and so for example, let's say you could have this atom of one type, this atom of another type, okay, this atom of another type. So you can imagine if I invert it, it doesn't look the same. Okay. So some examples are, for example, gallium arsenide, lithium niobate. There are more complicated materials like potassium, titanyl, phosphate. I think. So these are potassium, titanyl. So it has it's a compound of titanium and then some phosphate groups. So these are some very complicated materials with a lot of atoms and some complicated crystal structure which don't obey this property of centrosymmetry or inversion symmetry. Okay. So basically, let's say you have a material like this. I apply some fields, I get a polarization. Now let's say I do this inversion, right? So what happens? It's basically like flipping your coordinate system, right? So from the material viewpoint, all my fields are flipped. So this becomes minus EJ, this becomes minus EK, this becomes minus PI. Okay. So if the material is centrosymmetric, then it also has to obey this equation. Because there is no difference between them, right? Basically plus or minus doesn't matter. But you can see that this equation, these two minuses cancel out. So from the second equation, basically you get the negative of the first. Right? So this is equation number 1, and then equation number 2 is right, this to the minus sign. And the centrosymmetric material has to satisfy both of them. And the only way both of them can be satisfied, right, it's like A equal to B and A equal to minus B. Right? So only if B is 0. Right? Or so the only term which is the material dependent term here is this. So for centrosymmetric materials, chi2 is 0. Okay, I hope that's clear. Okay, so most materials which obey this property of inversion symmetry, chi2 actually vanishes. Only special materials, some special materials are there where which don't have this inversion symmetry, which break centrosymmetricity. There you have chi2. Okay? So all the chi2 work is done in a handful of materials. Okay? So if you look at what are 50 years of chi2 work, all of them are, you can list out the materials like You can count them on the fingers of your hand, 5 or 6. Right? Whereas Chi3 has no such restriction. Okay? You can check. You can try to argue like this and convince yourself that Chi3 is present in all materials. Even in centrosymmetric or non-centrosymmetric, doesn't matter. Chi3 in general will be non-zero or finite. Okay, so Chi3 will in general present in all materials. And the focus of our course would be Chi3. Okay, and that's also a reason for calling it photonics. So some of you might know that there's a course called Nonlinear Optics being offered in the physics department. So that course, like roughly half or more of the course would discuss actually the second order. And right towards the end of the course we'll discuss the third order. But here, all of our course will focus just on Chi3. Okay? And that's why I called it Nonlinear Photonics. So photonics usually refers to some guided structure, right? So when you confine optical waves to some guided structures, like optical fibers or waveguides, that field is usually called photonics. Right? So most of that kind of work is done only in Chi3. Right? So one of the reasons is that these materials are very complicated and it's very difficult to make fibers or waveguides out of them. So typically, these materials are just used as bulk, right? And we just focus laser beams into them. So to see Chi3 effects, you do that kind of thing. But we'll see that using like fibers or waveguides, you can really enhance the intensity first of all, right? You confine the light to a very small cross section. So the optical mode is very confined. And then it also can propagate over a long length, right? Depending on the length of the fiber or waveguide. So typically, like if you take a bulk material, you focus a laser. The smaller you focus, the faster it diffracts away also, right? So the interaction length is very limited. But with fibers or waveguides, you can have long interaction lengths. That's the advantage. But basically, any material that you can make a waveguide or fiber out of is usually centrosymmetric and has the first nonlinear effect is Chi3. Okay. So we won't be talking about Chi2 anymore. We look at Chi3. What order term? Right. In general, the polarization induced in the some direction I. It should be the product of the fields applied in some direction J, K, L, corresponding, and then the corresponding tensor element of Chi3. And then if you have fields in more than one direction and multiple directions, multiple fields, then you just sum over all the terms which are. So typically we do these interactions using lasers, right? So monochromatic fields, for example. We'll discuss some variations towards the end of the course, but typically all the fields are monochromatic, right, at some particular frequency. So I can write, so in general these are some fast time varying quantities, right, at the optical frequency. So typically I can write my polarization as, so let's say if it's at some particular frequency omega n, right? So I can write it like as a Fourier component, right? At omega n times the sinusoidal wave at omega n, right? CC denotes complex conjugate to make it real. Right? Electric fields also, and in general you could have like different frequencies. Right? You could have like a bunch of frequencies, so different ends. Similarly, electric field. So depending on the frequencies of the laser beams interacting, for example, those frequencies will be present, right? So you can see that I can write each of these electric fields in terms of their frequency components, right, or their Fourier coefficients. Then, so each of these would have different frequencies. So you can see that they will add up or subtract because you have complex conjugates also here, right, to give me the frequency of the polarization, right? So let's say I take three different frequencies here, right? So this is, let's say, some omega naught, this is omega n, and this is omega m. Right? So if I look at, so basically what I'm doing here is this omega. So for EJ it's omega naught here, right? For EK it's omega n here, right? And you have the complex conjugate. So you can see that the terms that can come in the polarization here. So one term could be, for example, at the sum of the frequencies, right? So you have e to the I omega naught t here, e to the I omega n t here, e to the I omega m t here. So you add, when you multiply the exponentials, the frequencies add. So, for example, you could have a term, and if I write the left hand side like this, then I can just compare the exponential terms, right, and equate the coefficients. So you could have a term which goes as the sum of the frequencies, right? So that, for example, I could write let me get rid of this summation for now. Just say so I could get omega naught plus omega m plus omega n in multiple ways, right? So one way is, for example, if the field in the j direction is omega naught, field in the k direction is omega n, field in the l direction is omega n. But I could have permutations, right? Because all I care is that the sum is omega naught, omega n, omega n. So I could have combinations like omega n, omega naught, omega n, right? Omega n, omega n, right? So you can have all those combinations, right? So those are the number of permutations of the different frequencies, right? So I denote that by d, which is some degeneracy factor. It's basically the number of permutations of the frequencies present in my medium, right? Times this. Okay, right? So the so this is third order correlation. So in general, you have product of 3 electric fields for the third order polarization, right? Then you have the corresponding tensor element of the type 3, depending on which direction you're looking at. And then you'll have some degeneracy factor depending on the number of permutations. Right? So to look at some examples, so let's say I have only one input field, right? Which means I have only one input frequency. So I just have a monochromatic wave at frequency omega entering my medium. So there's only one frequency present, which means all these are equal, right? So let's say I have some factory medium here, I have some laser beam entering, and this has frequency omega. Okay? So all these components have to come from this same laser beam, which has frequency omega, right? So all of these can only be omega, right? Which means what? So all the 3 input fields have to have frequency omega. So what kind of frequencies can I get in my polarization? So this would, for example, give me the sum. Okay? So I'll have a polarization which is induced at 3 omega. Right? That I can write as and what would be the degeneracy factor for this case? It will only be 1 because there's only one permutation, omega, omega, omega. Right? There's no other permutation. I can't rearrange it in any case. If that, yeah, I can. There's no other combination which can be with you. Okay?
Can I ask a question?
Yes, go ahead.
Sir, you have written the electric field at E of omega n used for my eta omega n t. So is the amplitude a function of frequency? So it is a decaying electric field, damped electric field, sir.
Why are you saying damped? Because this is a pure exponential, right? I omega.
But you have taken the electric field amplitude to be dependent on the frequency.
Yeah, so this is just some amplitude, right? So for example, you could have, I could send 2 lasers into my medium, right? At let's say omega 1 and omega 2. Then I would write this as E of omega 1 times e to the I omega 1 t plus E of omega 2, and then E of omega 1 is the amplitude of laser 1, E of omega 2 is the amplitude of laser 2, right?
Okay, I got it, sir. Thank you.
Yeah. I mean, damped would happen if now this frequency somehow becomes complex, right? Only then you get an example. But we are only talking about real fields. Real frequency. So, right? So, this factor will be 1 for this case. And what does this represent? So, I have 3 input fields at omega, which is giving me an output at 3 omega. Right? So I can sort of picture it as what's happening is so you can draw these level diagrams, right? So it's somewhat like the photon picture of the interaction. Okay? So you can imagine like the length of this arrow is like the energy of the photon, which is h cross omega, right? So it's proportional to omega. So I have 3 omega plus omega adding, which gives me 3 omega out. Okay. So this would be, for example, third harmonic. What is called third harmonic generation. Right. So you're tripling the input frequency or making the wavelength 1/3. Right. So that is, for example, one process that you have. another, since we have, remember we have complex conjugates here, right? So I could take the complex conjugate part here, and then I get minus sign here, right? Because this will become minus sign. Is that clear? So to explicitly write it, I will write this as E of omega n e to the minus I omega n t plus E conjugate omega n e to the I omega n. Right? So this whole thing is a real quantity. So for example, for some of these, or like let's say one of these three terms, I could take the conjugate part, but for the other two, I would take the other part, right? So you could have minus signs somewhere here, right, depending on where you take the conjugate. So for example, so if omega naught, so the first two terms I take from the first part, but the third, the omega m, I take the conjugate part, so that will be minus omega in terms of the exponential frequencies we are looking at right here. So then omega naught plus omega m plus omega n, you can see will be omega. Right? So here you are getting the output also at omega. Right? So in this level kind of picture, if I want to describe it, so now two of the frequencies are omega, right? So I'm adding omega and omega, but then I'm adding minus omega. So minus omega is like subtracting omega. So I come back down one, right? And I end up here. So my output is that omega. Okay. So basically, you draw the arrows or the levels corresponding to the input fields, and then what is remaining is the output coming out, right? In this case, I added omega, 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 and then it was 3 omega was remaining to come back to my original state, so that 3 omega is the output. Here you can see that omega, omega and minus omega, so omega is the output. Okay. So this is some sort of nonlinear process where I'm not generating any new frequency actually, right? Because the output frequency is also omega. But it's still nonlinear process in the sense it's different from the linear case, right? So the linear susceptibility will give me absorption or refractive index, phase shift, right? But this would give me some other effects which we'll study in detail later. But you can see that this is one nonlinear process where so the output frequency is omega. And what is the degeneracy factor for this case now? Right, so now I have three frequencies, two of which are omega, and third is minus omega. How many ways can I write it? Right, so I can write omega, omega, minus omega, or omega, minus omega, omega, or minus omega, omega. Okay. So there are three possible combinations. So this degeneracy factor here is 3. Right? What that is basically saying is how can I get an output frequency omega? I can get in 3 different ways. One way is this. Another way is I go up first, come back down, go up again, right? And then this is my output, right? So this will be the omega minus omega omega case. Or I could, for example, minus omega first and then Right? That will be this last. So I have three different ways of getting this output frequency omega. So that's why I have this degeneration factor 3. Okay. And so the expression for this would be, so I have the third order polarization, which is at frequency omega. Right? The output frequency is also omega. And then I have this, so I have a factor of 3 epsilon naught. And then I have the tensor, corresponding tensor element, whatever it is, for that particular configuration. And then here, remember that, so the term corresponding to the minus will be conjugate. Right? So if I take omega m into minus omega m, then the term here is actually E conjugate. Right? So you're getting E conjugate. So E conjugate is mod E square, right? So you're getting something like this. But here, so I mean, let's say to simplify matters, I'm looking all of them in the same index, let's say. Right? So for example, J, let's say I'm looking all of them at the same index or something. So it's the same field which is coming 2 times as the real part and or like as the primary part, and then one of them is the conjugate. So you get mod E square times. Okay, so here you get something like EQ. Right, so here E of 3 omega is proportionally EQ at E omega cube. Whereas here I get P omega, which is proportional to mod E square. Okay, and you can see that. So remember, the linear case is just this. The polarization is proportional to the field. So here, if I club this whole thing inside, it looks somewhat like, right? So this is E, and I can define, if I define chi effective as, let's say, 3 chi 3 times mod E square, it looks like this, except this chi is not chi effective. And you can see that's actually proportional to mod E square, which is the intensity. Okay, so this is something like an intensity dependent susceptibility, or which translates to intensity dependent refractive index. We'll see. Okay. So this is actually what is called intensity dependent refractive index. Okay. That clear? Any questions on whatever we've covered so far? Let's see. Okay. We will just start discussion of the next topic. So, if you look microscopically, right, where is this nonlinear response coming from? Right. So, if we zoom into like the atomic level, right. So, typically, um, if you look at the atom, there's a nucleus, there's electron cloud around it, right? And then when we apply an electromagnetic field, uh, that applies a force on the charges, right? So it separates the positive and negative charge. So the electron cloud is pulled apart from the nucleus, and you induce a dipole, right? And typically, what happens is, so my input wave is at some particular frequency, right? So, right. So it's a laser. Let's say it's at some particular wavelength or frequency. So the electric field is oscillating at that frequency, and then this charge separation is also oscillating at that frequency, right? And now you have charges which are oscillating or accelerating at that particular frequency, which radiate fields again at that same frequency, right? So this is sort of the linear response of the medium, right? So whatever happens is just modifies the input field, like absorption or scattering or effects like refractive index, etc., right? So we can sort of model the nonlinear response in a similar manner. So the question is, where does optical nonlinearity come from fundamentally? Right. So typically, in the classical regime, we can model the atom as some electron which is attached to the nucleus by some spring. Right, so this thing is my atom. Right, so I can typically model it as a classical harmonic oscillator. With mass attached or charge attached to a spring. Right? But typically we model it as a harmonic oscillator. Okay. So if you go back to your simple harmonic motion, right, that means like the force, the restoring force that this spring, a fictitious spring, is exerting on the electron is like a normal spring, which means like if you have some displacement here, x, then the force is proportional to x, right? So F is equal to kx or minus kx in the opposite direction, right? That is a harmonic oscillator. But what happens when, so this, where is the displacement coming from? This is coming from my input wave, right, which has some electric field. So that electric field applies a Lorentz force on this electron, let's say, right, and that pulls apart the electron by some distance, and there's a restoring force back towards it, right? So now you can imagine if this electric field is really large, then the force can be large, and this displacements can go big. Okay. So let's say the displacement goes, now becomes comparable, let's say, to the atomic radius. So you're distorting the atomic cloud, right, appreciably. Then you can imagine this restoring force, let's say, is no longer harmonic, right? This relation does not hold, and maybe you start having some higher order terms once you distort it too much, right? It's like pulling a spring to beyond its elastic limit, right? So then this would become an harmonic oscillator, or a nonlinear oscillator, right? And fundamentally, that is what will give you the nonlinear optical response of the entire network. Okay. So what's happening is that for high powers or high intensities of my input field, the electric field is large enough to pull the electronic cloud far enough that there's a distortion in the electronic cloud, right? And the restoring force no longer remains linear. So the atom no longer remains a harmonic oscillator, but becomes an anharmonic oscillator. Okay. Of course, this is a classical model, right? You can take a quantum mechanical model where the atom is not a spring, right? So this is sometimes called the Lorentz 2D model of the atom. This is a classical model. But you can take a full quantum mechanical model, right? You can take the wave function of the atom, you can take discrete energy levels for the atom. So you can do a semi-classical analysis where the field is of course taken as a classical field, right? Some harmonic field like what we wrote. And then you treat the atom quantum mechanically, right? And then you can write a effective Hamiltonian and then do perturbation theory and then solve it like that. And basically the perturbation theory is giving you the extra terms. Okay. So I mean we'll discuss just the simple classical model because that gives exactly the same results as the more complicated quantum model. But if you want to go into the quantum model, I mean I refer to you the relevant chapter in the textbook. But basically the classical model works just fine and it gives very accurate results. But yeah, so the analogy is basically the perturbation, the higher order perturbation terms in the quantum mechanical theory correspond to these higher order terms here in the classical model. Right? So if we analyze such a case, right, we have some incident electromagnetic field and then the atom is causing some displacement in the electronic cloud and then some disturbing force. So we can write an equation of motion for the electron here. Okay. So the total force, which is the mass times acceleration for the electron, will have I guess 3 components. One is just the Lorentz force from my input wave, right? The electric field. It also has a magnetic field, right? So that will impart a Lorentz force on the electron. Then there will be a restoring force, which is due to this attraction back to the nucleus, right? So fundamentally, it's an electrostatic force, but you can model it as a spring, right? So this is true. This first term is a good approximation for small displacements, and you could also include some damping. Right. So typically in a mass spring system or a harmonic oscillator system, you could also include some damping, which is friction. Right. In this case, where is the friction coming from? So you go back to the quantum mechanical picture, right? So you have processes like, so you have some discrete energy levels in this atom, right? So the atom can go from one energy level to another. But then if it, let's say, goes to a higher energy level, it does not stay there, right? There are decay processes like spontaneous emission, and it comes back to the ground state, right? So these quantum mechanical decay processes like spontaneous emission are what are we modeled as the damping term in this case, right? Right. So if x is the displacement of the electron, then acceleration is the double derivative. So again, I put a tilde to denote rapidly varying quantity, right? So this is varying at some optical frequency omega. The position is also varying at that same frequency, etc. So the double derivative, then the damping term, which goes as the velocity times the damping constant, plus the restoring force, right? So m times this is ma. Then what is given? So we include the damping, the restoring, then the Lorentz force is the Lorentz force, charge times the electric field. All right. So this is a familiar equation of a damped harmonic oscillator, or damped, simple harmonic oscillator, right? And this is some driving term which I am getting from external field, right? So this k here is m omega naught square. Right. So if you know the Lorentz force, typically we write it as Q times E plus B cross B, right? And there's also a magnetic part, and this electron is actually moving. Right? It has a velocity component, so it's actually moving. So ideally, we should take the B cross B part also, because my input electromagnetic wave also has a magnetic field. But typically, we can neglect the magnetic component. Can you guess why? So typically, we just neglect this term and just keep the electric field. So if you remember, if you have some plane wave incident, right, let's say in free space, then the magnitude of the electric field, or let's say the magnitude of the magnetic field, is related to the magnitude of the electric field by this factor. So 1 over the speed of light times, right? I hope this is very familiar, right? So if you take a plane wave, so typically you get B as something like K cross E over omega or something, right? From Maxwell's equation, if we just take a plane wave and then relate the magnetic and electric fields, right? So you can write it like that. The magnitude of the B field would be the magnitude of the E field divided by the speed of light, right? So you can see that the second term will have magnitude something like B over C times the magnitude of the first term. Right? So if I put B as E over C, and the first term is proportional to E, but the second term is proportional to B over C times E. So if B is much smaller than C, then this magnetic term is much smaller than the electric term. Okay. So unless the electron is moving at relativistic velocities, you can basically ignore it, right? And that's true in most cases, right? So for the most part, the intensities of lasers that we use, the velocities that the electron moves at is much smaller than C, and we can neglect that. There are some special cases where actually this term becomes important, but for the most part, especially for the photonics, nonlinear photonics applications that we'll be looking at, this term is negligible. Okay. So only for very high electric fields. So once you start approaching the atomic electric field, then the velocity starts approaching C, and then this term becomes important. Okay. But otherwise, first one. Okay, so that's sort of this classical harmonic oscillator model, right? And if you analyze this is what will give you like refractive index, absorption, etc. Right? But so the restoring force here is just the normal linear restoring force. But if you include, let's say, higher order terms here, right? So F restoring, I can write, let's say, as minus m omega naught square x, that's the linear term. But let's say I include higher order terms. So I can define a potential in which the electron is sitting, right, as f times integral of f dx. I can define the potential u of x, right? So the u is some potential that the electron is sitting in, some potential well, and I displace it by x, and then there is some restoring force, right? So you can see for a linear restoring force, u of w proportional to x squared, which means it's sitting in a perfect harmonic well, right, a quadratic potential. But if you have other higher order terms, this shape will start getting distorted. Okay, which is what is related to this distortion of the electronic cloud. So for small displacement, the potential is well modeled by a parabolic potential, which is the case for a simple harmonic oscillator. But once the displacements become large, so you can imagine this is some complicated potential, but for small displacement, it looks very much like a parabola. Okay, so that's why you can say for low laser intensities, the linear case, it's well modeled by a simple harmonic oscillator, but once you start displacing it more, then it becomes not a parabola, and nonlinear effects start appearing. Okay. So we'll stop here and then continue next time and see how this non-anharmonic potential gives rise to nonlinear terms in the susceptibility finally. Starting from this microscopic atomic picture, how do we get to the chi values?
Sir,
Okay.
sir.
Yeah?
Sir, we have written the force expression for the whole system. So there will be force from the atom on the electromagnetic field. So where is that
Force of what?
force from the atom on the electric field?
So this is the force that the electron is experiencing.
Okay.
Right? So we are writing the equation of motion for the electrons.
Okay.
So it's experiencing a force from the electromagnetic wave, a restoring force from the nucleus, right, and a damping.
Okay.
Those are the three forces. This is action. Okay, so we'll end here, and so all this is given in chapter 1 of Boyle.